has points, yes. It has like edges, like sides. It has faces, right? So do you want to count real quick how many points we have on that? 8, yeah. How many edges? 12. And how many faces?
6.
What do you get? 2.
It's crazy.
Right. So a lot of the real here, and the reason why is because we can actually draw this as a planar graph. What else did I bring? You guys seen this before? Yeah? All right. You do the same thing. Want to count it? How many vertices do we have?
6 vertices.
Yes. How many edges?
9.
Okay. How many faces?
5 faces.
Is that 2?
Yeah.
Okay, cool. Yes, question.
Can you draw like these
As a graph. Great question. So let's draw this one. Can I erase this? Is that okay with you guys? Okay. So yeah, okay. Basically, like, the reason why is because of Euler's fact, right? And the reason, and because we can actually draw these as planar graphs. So let's picture this. We have 6 points on this. Okay. So we have. I'll draw them big. So we have this one, this one, this one. On this side we have 3. So 1, 2, 3. On this side we also have 3. 1, 2, 3. 1, 2, 3. Now let's draw on the edges. So this point and that point, they share an edge, right? So we draw across. This point and that point, they share an edge, so this goes across. And that share an edge, so they go across. And then we can see that there's like a triangle on this side, right? So that means that these 3 are in a triangle fashion. And so are these 3. Does that look like Toblerone kind of? No? No? All right, fine. I'm not an artist. Do I have 9? 1, 2, 3, 4, 5. Yeah. Okay. So this would be the graph representation of this object, right? And you can see the actual faces. Like there's 1 here, 1 here, 1 here, 1 there, right? 1, 2, 3, 4. And then there's 1 on the back. The back is the whole rest of the board. Because like we can't actually see the back. But yes, that is. See, we can see like this is like a relationship we can find in many objects because we can actually draw them as planar graphs. And I know I'm kind of running over time. Let me just do one last example. It'll be really quick. So, soccer ball. Same idea. How many phases are on the soccer ball? To count, it would take forever. Infinite, yeah. But soccer ball has vertices, points, has edges, right? And so, if you knew how many vertices and edges this had, you can easily calculate the number of faces. So, in a soccer ball, this isn't a real soccer ball; it's like fluffy and stuff, but that's okay. Vertices, there are 60. Edges, there are actually 90. So how many faces are there on a soccer ball? Yes?
28.
Not quite. I'll have to do my math real quick. Yeah, well, let's try that. Let's try this together. Okay, so we have 60 minus 90 plus 2.
32.
So 32, right?
Yes.
Yes, okay. So there are actually 32 faces. And you can get that straight from graph theory. And actually, when, so this is just a soccer ball to us, like normal people. But there's actually like, if you guys are interested in chemistry, there's this famous molecule, it's called a buckyball. Okay, I can write out the board. And it's exactly like a soccer ball. It's like the skeleton of a soccer ball. It has like these 60 vertices. Its formula is carbon 60 for those of you who know chemistry. I mean, that just means that there's 60 carbon atoms on it. And that's how we know that it's like exactly like a soccer ball. Because, and so that molecule It's a really big molecule, right? It's like 60 carbons. Like water only has like 3. And so that molecule follows exactly the structure of a soccer ball. And one of the reasons that we know that is because we know that it has 60 carbon atoms, and we know that it is hollow in the sense that it encloses space. Like water is an enclosed space, but there's space inside of it, right? And so one of the reasons that we know why it's like a soccer ball is because we can use graph theory and say, oh, because it has 60 carbon atoms and because it's hollow, really the only way that could actually end up happening in like a symmetric fashion is if it were like a soccer ball. So yeah, that's a more like complicated example of how we can eventually apply graph theory to like not just like everyday life, but like other subjects as well. But anyways, that would be the end of my lecture. I hope you guys enjoyed it. If you guys have any questions, I'd be happy to stick around and answer them. But I hope you guys enjoyed graph theory. And I have like, if you guys want to learn more about it, I can definitely give you guys like a few references and stuff. And if you guys have questions about discrete math in general or anything, like, sure, feel free to talk to me. So, okay, great, thanks.
Thank you, Alex, for coming and spending your time with us. Your presentation was very informative. Thank you, everyone in the audience, for your time. We hope to thank you, Jen Lemke, for helping us with this presentation, helping us. Yeah. If you're interested in things like this, Knowledge Unbound is during the summer we'll teach programming, and if you are interested, you can go check the library schedule. So thank you and good night.